Hello, everyone. I'm Shane. Welcome to my thesis defense. Today, I'll be presenting structured cooperative multi-agent coordination. I'll first introduce the background and the motivations of the thesis. Then I'll go through 3 contributions. Finally, I'll summarize my presentation and conclude with recommendations for future research directions. A multi-agent system describes multiple distributed agents which takes decisions autonomously and interact within a shared environment. Different from single-agent reinforcement learning, multi-agent reinforcement learning involves multi-agent systems. Each agent seeks to accomplish an assigned goal for which a broad set of skills are required to build intelligent behaviors. Depending on the task, an intricate interplay between agents can occur such that the agents start to collaborate or act competitively. Here we'll focus on a team of agents coordinating together to achieve a shared objective cooperatively. We formalize the problem as a DEC-POM-DP. Multi-agent reinforcement learning has many representative application areas, including autonomous driving, gameplay, drone swarm control, and collision avoidance. Multi-agent reinforcement learning can solve teamwork that requires coordination. However, there are still many challenges in multi-agent reinforcement learning. First, the scalability problem. Since in multi-agent reinforcement learning, we need to train multiple agents concurrently. The size of the joint action space can grow exponentially with the number of agents in centralized approaches, which is known as the curse of dimensionality. Second, the partial observability problem. In real world, full observability is rarely available for each individual agent. The information insufficiency poses difficulties for achieving effective coordination. Lastly, the non-stationarity problem. In a multi-agent system, other agents are a part of the environment for each agent. The involvement of agents causes non-stationary environment dynamics, which breaks the Markov property assumption of reinforcement learning algorithms. In addition, the random exploration of other agents can confound the reward signals of an agent. This is a game theory pathology referred to as the relative overgeneralization. These are the common solution approaches to multi-agent reinforcement learning. On the left, centralized training and centralized execution, or CTCE. In this approach, agents are treated as one joint agent. There is a joint policy for all of the agents. In the middle is decentralized training and decentralized execution, or DICG-DE. In this approach, each agent learns independently, and each agent updates its own individual policy. On the right side is centralized training and decentralized execution, or CTDE. In this approach, agents only exchange additional information during training, which is then discarded at execution time. CTDE has become the most popular training scheme in multi-agent reinforcement learning. However, these common approaches are often not optimal for tasks that require high coordination. In addition to the 3 common solution approaches, network and communication-based approaches have become popular. Coordination through communication is the behavioral pattern of humans. This class of approaches learn emergent communication protocols for information sharing. Communication messages serve as observation augmentation for each agent, providing additional information for their coordinated decision-making. We consider communication approaches as partially centralized execution. The main research question of this thesis is that, can we find effective and efficient coordination for all the agents in cooperative multi-agent reinforcement learning? Centralized approaches can often be optimal, but hard to solve in larger scale domains. And decentralized approaches are feasible to solve, but often suboptimal. We want to find a balanced method. Exploiting the physical structures of multi-agent reinforcement learning problems can give us better solutions. In my contributions, I use distance-based multi-agent value decomposition, graph structure, communication models, and etc. to solve the problems. Now I'll talk my first contribution, improving utility fusion with deep correction. My first contribution involves optimizing collision avoidance in dense airspace using reinforcement learning. Collision avoidance is a representative application area of multi-agent reinforcement learning. The problem setting is that in the future, airspace might become very crowded. Existing methods often consider a single intruder. We need a reliable solution for collision avoidance facing multiple reactive intruders. Our contribution are that we solve multi-agent collision avoidance problem from single agent's perspective using a decentralized approach. And we use deep correction to improve the conventional method. There are many existing methods for multi-agent collision avoidance. The geometry-based method, optimal reciprocal collision avoidance, or ORCA, has been exceptionally successful. ORCA and its extensions use heuristics to construct a complex model for the collision avoidance policy, which has many parameters that are difficult to tune. Besides, these methods are sensitive to the uncertainties in the real-world scenarios, since they assume each agent to have perfect sensing about other agents' positions and velocities. While value lookup table-based collision avoidance systems like ACAS-X has also been adapted to multi-agent operations. It is safe and robust and can handle uncertainties. However, ACAS-X is optimized for resolving pairwise encounters. It can operate in low-density airspace, but it can possibly be over-conservative with multiple intruders. Neither of the two methods are optimized for dense airspace operations. Let's see how a value lookup table-based collision avoidance system deals with multiple intruders. We define the intruder as the aircraft run into the surveillance range of the own ship. We first do utility decomposition to divide the multi-intruder encounter into pairwise encounters. Then we can obtain pairwise utilities for actions, denoted as Q1 to Qn. Then we do utility fusion to add up the pairwise utilities to obtain Q low, which is a low fidelity approximation of the truly optimal Q values. We decide on actions by taking argmax over Q low. Then in this way, all the intruders are considered. Since each pairwise policy is solved by value iteration, we name this method VICAS. The utility fusion of VICAS for multi-intruders is implemented in two ways. The first one uses the closest intruder in fusion, which is a very rough approximation named VICAS closest. The second one uses all the intruders and takes the minimum Q value of each action. This considers the most dangerous intruders for each action. So it is risk averse, and it is named VICAS multi. Then let me introduce what's deep correction. This is an idea borrowed from multi-fidelity optimization. When the high fidelity model is expensive to evaluate, we approximate it by adding a correction term to a low fidelity model to get a surrogate. In our problem, the high fidelity model is the global optimal Q values, which are hard to solve for directly because of the multi-agent scenario. The low fidelity model is the Q low, which is the approximation from utility decomposition and fusion. By adding a correction term delta to Q low, we have a chance to approximate the global Q values in a better way. Delta can be a deep Q network or DQN. That is why we named the method deep correction. And why we use deep correction? The reasons are that the global Q values are hard to optimize directly, especially in a multi-agent setting. And Q low is easy to obtain by using utility decomposition and fusion, which can provide a stable starting point of reinforcement learning. And finally, deep Q network is a powerful value approximator. These are the sample trajectories of our collision avoidance systems. The scenario here is a near mid-air collision being inevitable if there's no collision avoidance system. The sample trajectory of VICAS multi are winding and inefficient. And there are oscillations in actions. The winding route can be a cause of congestion in the airspace. And the route of VICAS closest are less winding, but we can do better with deep correction. In contrast, the corrected collision avoidance systems are able to ensure safety with much less maneuvers, keeping the route straightforward and efficient. This Pareto frontier plot shows the trade-off between safety and efficiency for various approaches under different aircraft takeoff rates. The corrected collision avoidance systems are corresponding with the best performing points at the bottom left corner of the Pareto frontiers. To give a summary for this contribution, we use utility decomposition fusion to solve a multi-agent problem from single agent's perspective. And we use a deep Q network as a correction term, which is trained by deep Q learning. And both safety and efficiency are improved in dense airspace with deep correction. Now I'll proceed to the second contribution. The second contribution is deep implicit coordination graphs, or DICG. The problem we try to solve is that agents with limited observation need communication to coordinate with each other. Existing approaches often use hard-coded ways or distance thresholding to build binary coordination graphs. We use self-attention to dynamically build soft-edged implicit coordination graphs. Then we use graph convolution networks to pass information between agents. There are some related work in solving multi-agent coordination. First of all, the parameter sharing decentralized approaches. For example, the Ph.D. of TRPO. It is fast, scalable, but suboptimal due to partial observability and decentralization. The second class of approaches use value function decomposition. For example, VDN and QMix. They reason about joint value function by decomposing it according to the locality of interaction. However, they do not have cross-agent information sharing or communication. The newest class of approaches borrow the idea of graph. They often use distance thresholding or hard-coding method to build graphs. For example, DICG has formal reasoning about joint action given the graph structure, and DGN and ATOC use distance-based graph for communication. We try to use self-attention to achieve dynamic graph building instead of hard-coded or distance thresholding methods. Now, effective multi-agent reinforcement learning in cooperative environments requires coordination between agents. There are two extremes in achieving multi-agent coordination. Let's have a recap of common solution approaches. A straightforward way would be reducing the problem into a larger, fully centralized problem, where the action space of the joint action space is the joint action space of all the agents. This can provide optimal solutions and better coordination in relatively small domains. Unfortunately, the joint action space grows exponentially with the number of agents, making it intractable for many domains. Another extreme is to fully decentralize the problem. Then the exploding joint action space is no longer a concern. However, such decentralization can be suboptimal. The optimal policy is often not learnable in such a context due to the game theory pathology referred to as relative overgeneralization, where the agent's reward gets confounded by penalties from the random exploration of other collaborating agents. In addition, during learning, a decentralized agent suffers from non-stationarity of the environment dynamics caused by other agents and the lack of information from the other agents. We desire to find a balanced middle ground between these two extremes. For several multi-agent domains, the outcome of an agent's action often depends only on a subset of other agents in the domain. This locality of interaction can be encoded in the form of a coordination graph. Best actions are selected from factored representations via Bayesian network inference-inspired algorithms like variable elimination and max plus. Previous work explored the use of coordination graph in the context of tabular reinforcement learning, while deep coordination graphs extended these ideas of factoring the joint value function of all agents according to a static coordination graph into payoffs between pairs of agents. They did so by estimating the payoff functions using neural network and using message passing based on max plus along the coordination graph to maximize the value function, allowing training of the value function end to end. Another technique to mention is self-attention. It emerged from the natural language processing community. It is used to relate different parts of inputs. It has been applied to multi-agent reinforcement learning to learn the relative importance of agents. Self-attention is a form of content-based addressing. Given queries and a set of keys, it can find similar keys based on some distance metric. For graphs, the interaction or coordination between nodes can be modeled as attention weights. In deep learning, graph neural network is a popular class of architecture that passes information along the edge of a graph to learn better structured representation. Graph convolution has graph structure as adjacency matrix and the node features as feature matrix. It passes messages between pairs of nodes by aggregation and meanwhile refines the node representation in the process. For example, the node B here aggregate information from its neighbors, node A and C, and perform this recursively. Now I'll introduce our approach in the following slides. Starting from agents of local observations, OI, they are parallelly passed through a parameter sharing encoder to get the initial embeddings, observation embeddings, EI, and they are stacked into a feature matrix denoted as capital E. The self-attention module then uses the observation embeddings to compute the relative weights of agents to each other. We use self-attention to dynamically build coordination graph. Self-attention weights can be used to softly weigh the edges of a coordination graph. We replace the discrete binary adjacency matrix with the attention weight matrix. In this case, a coordination graph becomes implicit. With the implicit coordination graphs computed by self-attention, we can use graph convolution network for several runs to communicate information across agents. Both self-attention and graph convolution are efficient and differentiable operations, making end-to-end learning feasible. And a residual connection is used to add or concatenate the non-communicated initial embeddings, E0, with the communicated embeddings, EM, producing a final embedding, E tilde. In the actor critic context, the final embeddings, E tilde, can be directly fed through a parameter sharing policy to get actions for centralized execution. The final embeddings, E tilde, can also be used to train the centralized critic or value function for decentralized execution. In summary, the deep implicit coordination graph, or DICG, can be used for both centralized and decentralized execution. In the back end, we use proximal policy optimization, or PPO, a policy gradient algorithm to train the network. Now I'll show experiment results and analysis of DICG in the following two environments: predator-prey and StarCraft multi-agent challenges, or SMAC. These are results of the predator-prey environment. The highlight of the predator-prey environment is that apart from regular step cost and capture reward, we impose a special penalty to penalize any single agent capture attempt, which means at least 2 or more predators agents are needed to make a successful capture. Otherwise, a capture will be given and the capture will not be successful. So high collaboration is therefore required to achieve a high return on such setup. The 4 plots here show the training curves of increasing single agent capture penalty from 0 to 1.5. The centralized execution version of DICG, denoted as DICG-CE, in blue curves, performs the best, following by the decentralized execution DICG, denoted as DICG-DE, in red curves. They outperform the fully centralized and fully decentralized baselines. To understand how the DICG learns to coordinate, we perform attention weight analysis. We study the strengths of soft edges of the implicit coordination graph. A natural heuristic of what affects the strengths of connection between agents is the distance between agents. These figures show the relationship between the attention weight learned by DICG and the distance between agents. The 0 distance here corresponds to the attention weight of an agent to itself. We can see in the beginning, the attention weight naturally decreases as the distance between agents increases. As the penalty increases, agents tend to increase the attention weights towards agents further away. This phenomenon coincides with the coordination requirements imposed by the increase of penalty that agents should pay more attention to form groups with each other to capture prey as a team rather than moving alone. To examine whether information is effectively communicated across the agents along the implicit coordination graph, we designed a small experiment to predict agent J's action, AJ, using agent I's information, where I does not equal to J. Theoretically, with a finite amount of data, if given some input more correlated with the action of agent J, a supervised classifier can produce a higher prediction accuracy. Therefore, we use the pre-DICG embeddings and the post-DICG embeddings as inputs to compute, to compare with each other. We use a simple 2-layer multi-layer perceptron classifier. The results of 5 random agent pairs are shown in this plot. The post-DICG embeddings in the red curve can predict other agents' action with a higher accuracy than the pre-DICG embeddings in the blue curve. We can interpret this as the DICG architecture allows individual agents to learn other agents' action intentions. In this demo, we show the decentralized execution DICG agents in a SMAC environment. So we control these 3 red agents, and the computer AI controls these 5 smaller agents. The goal of the task is to eliminate the opponents. We can see that the agents successfully learn a divide and conquer strategy. They first split up and then use a hit and run tactic to take advantage of their higher moving speed over their opponents. You can see that they run along the edge of the map, since this is the longest geographically identifiable route on this plane map. So one observation proves that they are not totally decentralized is that when an agent finishes dealing with its own opponents, it comes to help other agents. can see, yeah, they are cooperating and helping each other. So in the end, they are able to finish the task successfully. This table compares the performance of DICG in some SMAC maps with other state-of-the-art approaches by the time DICG was published. Our approach showed comparable or better performance comparing with other approaches. In summary, inspired by coordination graph-based action inference, we designed a effective combination of self-attention and graph neural network for multi-agent reinforcement learning. The proposed approach works for both policy learning and as well as centralized critic learning. The model achieves state-of-the-art performance on a variety of domains with high coordination. Now I'll proceed to the third contribution. The third contribution is learning emergent discrete message communication. The problems are that DICG does not have explicit communication channels. Communicated messages are also implicit due to the use of graph convolution. We would like to see some interpretability in emergent communication. In this contribution, we come up with an explicit broadcasting-based communication model. The model sends discrete tokens between agents. We then conduct positive signaling and listen analysis on the model. And we further explore the feasibility of human-agent interaction. Explicit communication modeling has been there for a while. For example, ComNet and IC3net, the earliest multi-agent reinforcement learning communication work. They use simple mean message aggregation. And almost all the existing multi-agent communication approaches use continuous message, for example, Tarmac and ATOC. And previous work has tried to ground discrete messages to concrete meanings. However, it is only studied in simple two-agent image-based referential games. And we found that human-agent communication studies are rarely seen in multi-agent reinforcement learning. This is our explicit broadcast communication model. It first starts with an agent pair, I and J, with their observations OI and OJ. They are passed through a parameter sharing encoder to get observation embeddings, EI and EJ. From the embeddings, we use attention query encoder to compute the attention logits, CI and CJ. And we use a broadcast message sending encoder to obtain broadcast message logits, mu-I and mu-J. And like in DICG, self-attention is a go-to choice for aggregating information. We use multiplicative attention to compute the attention weights for the pair of agents. And we use a non-differentiable argmax operation to get discrete broadcast messages from logits. We then aggregate the broadcast messages in the public channel for each agent using weighted sum, which is weighted by each agent's attention weights. And finally, we concatenate the initial embeddings, the attention weights, the broadcast message logits, and the aggregated messages to form augmented embedding. They are passed through a parameter sharing policy to obtain actions. The concatenation makes sure that gradients can effectively flow back to each encoder during training, even though the argmax operation breaks a part of the computation graph. A very natural way of obtaining discrete messages is actually sampling from the Gumbo softmax. And it is what we tried first. However, experiments showed that it was very unstable and hard to train. We switched to taking argmax instead, sacrificing part of the differentiability, getting much stabler performance. It is essentially an extremely greedy way of sampling. We use two kinds of discrete message formulation. One is binary bit string with a length of n. It can represent 2 to the power of n distinct messages. It is obtained from taking argmax from an n by 2 logic matrix along the 2-dimensional axis. Another discrete message formulation is one hot vector. With a length of n, it can represent n distinct messages. It is obtained by taking argmax along the n-dimensional axis. As we did for DICG, we test the model with the predator-prey environment. And as before, we impose a penalty for non-cooperative single-agent capture attempt. Therefore, the locations of other agents and potentially their perception of prey are necessary information of each agent to cooperate and achieve high returns. However, this time, we focus on the effectiveness of communication approaches. We engineer the agent's observation so that we can remove other agents from an agent's observation. That means an agent can now only see the prey, but not the other agents. The combination of agent invisibility and a single agent capture attempt penalty makes the task a lot harder. The performance of all the communication approaches is bounded by 2 non-communication approaches. The upper bound here is non-communication with other agents visible, which is information sufficient for each agent. The lower bound here is non-communication with other agent invisible, and it is information insufficient. The X label here in the figure consists of 2 lines. The first line indicates the communication protocols. The first letter indicates the message type. C means continuous, B means bit string, and O means one hot. The number following the letter means the length of the messages. The second line below indicates the vocabulary size of each communication protocol. For all the communication approaches, agents are set to invisible. Then the performance heavily relies on the effectiveness of communication. Here, continuous message communication works the best. The size of continuous communication messages does not matter much according to experiments. It is easy to understand since even a scalar real number can represent an infinite number of messages. The 32-bit string works the best among the discrete communication, followed by the 16-bit string. They have high representational power since they each have very large vocabulary size, but they are still beyond humans' cognitive range. They're followed by the 64-dimensional one-hot message and other lower dimensional discrete messages. These are within humans' cognitive range, and their performance are not too far off. Oh, not finished. These experiments show that communication matters in such an information insufficient environment. And discrete messaging can do reasonably well by trading some performance with better interpretability. Here are some demo videos for the multi-worker environment. Multi-worker is a continuous control locomotion task. The domain consists of multiple bipedal walkers that can actuate the joints in each of their legs. At the start of each simulation, a package is placed on top of the walkers. The package is large enough that it stretches across all the agents, and it is too large for a single walker to move on its own. The walkers must learn how to move forward to coordinate with each other in order to keep the package balanced while navigating the terrain. On the left is a scenario where communication is turned off. Neighboring agents are set to invisible, and the turn LiDAR is also turned off. So theoretically, agents do not have enough information to achieve high return cooperatively. And as expected, they can do pretty bad without the sign of adequate coordination. In the middle is the scenario where communication is also turned off. but neighboring agents are set to visible, and the turn LiDAR is also turned on. So theoretically, the agents have enough information, local information, to perform well without communication. And the experiment results prove the anticipation. An interesting observation is that agents learn that 3 is not a good number to define the straight line. So they tend to finish the task using only 2 leading agents for better stability. On the right is a scenario where communication is set to using 8-bit string with a vocabulary size of 256. Neighboring agents are set to invisible, and the terrain LiDAR is also turned off. As already shown in the leftmost demo, this local information will not be enough to make good cooperative decisions. The demo shows that the 8-bit string can effectively help finish the task. We analyzed the positive listening and signaling of discrete messaging. Positive listening is the degree to which the received messages are influencing an agent's behaviors. Similar to DICG, we quantify this by training an action predictor for agent I that takes in the aggregated messages received by agent I. Note that we mask out the contribution of agent I itself from the aggregated message. And positive signaling is the degree to which an agent's sent messages are related to its behaviors. We quantify positive signaling by training an action predictor for agent I that takes in the message sent by agent I. As we can see in the 2 figures, continuous messaging has the best prediction accuracies overall. The bit string messaging can achieve comparable accuracies with continuous messaging using much smaller vocabulary size. And one-hot messaging has worse performance due to its limited representational capacity. Finally, we explored the feasibility of human-agent interaction using discrete messaging. First, we collect raw observation and message pairs from the trained agents. We cluster the raw observations using the TSNE algorithm. Then we label the raw observations with their corresponding discrete messages learned by the model. The figure on the right shows such clustering and labeling from the predator-prey environment with 4-bit string, which has a vocabulary size of 16. Different colors in the clustering means different discrete messages. We use this clustering plot as a reference. We observe that same cluster of raw observations tend to have the same discrete message labels, which is the same color. This provides an entry point for human-agent interaction. For human interaction process, we can project a new observation into the pre-known reference clusters using the TSNE algorithm, as shown by the red cross. And a human can empirically select the most probable message according to the reference clusters and broadcast it to other agents. In summary, in this contribution, we proposed an explicit broadcast-based communication model. The model achieved end-to-end trainable discrete token communication between agents. And we analyzed positive signaling and listening for the model. And at the end, we designed a human-agent interaction method based on the model. Now, let me summarize my presentation and conclude with recommendations for future research directions. Here, I'll give a quick summary for my thesis with a few takeaways. For the first contribution, improving utility fusion with deep correction, we use utility decomposition and fusion to solve multi-agent reinforcement learning problems from single agent's perspective. And we use a deep Q network as a correction term. For the second contribution, deep implicit coordination graphs, we use self-attention and graph neural networks to achieve effective coordination. Our proposed approach can be used for direct policy learning or critic learning. For the third contribution, learning emergent discrete communication, we propose an explicit broadcasting-based communication model. We achieved effective discrete token communication, and we performed thorough analysis for the model. Now I'll make some recommendations for the future research directions. First, interpretable communication. It is desirable to ground communication messages into concrete meanings, or even using natural language for communication. This will be very helpful for trust building with agents in ad hoc human-agent teaming and zero-shot coordinations. The second recommendation is explainable measurements of interaction. The measurements the research community has been using include distance and attention weights between agents. They are good, but not principled enough. There's a need for measurements that reason about the behavioral history or causal influence between agents. Finally, model-based multi-agent reinforcement learning. In human decision-making process, we maintain a belief about what others are going to do in the future. Similar for AI agents, we would like to have them coordinate actions according to a combination of historical experience, current observations, and the beliefs of future, where the beliefs of future will be relying on the model of other agents. Lastly, I would like to thank Airbus A-Cube and MIT Lincoln Lab for sponsoring my PhD program. They are great collaborators with endless research ideas and support.